Good day and welcome. Thank you for joining me at TD Physics today as we explore projectile motion with a horizontal launch. So we're going to start off by recognizing the physics classroom. That's where we're getting this particular animation from. Physicsclassroom.com, source of lots of really great resources. So here we see our projectile, in this case apparently a cannonball being launched from a cliff. This cliff would be fairly high in order for this to happen to get more than 10 seconds of hang time. If we launch it horizontally, you'll notice that the arrow pointed right, representing its horizontal velocity, remains the same. And you'll see down at the bottom that Vx, or our velocity in the horizontal component, is staying constant at 100 meters per second. While in the vertical component, while initially at 0, because it's launched horizontally, as time goes on, acceleration due to gravity results in a greater and greater vertical velocity. So projectile motion results in an object that is going to trace a parabolic path, and the purpose of our analysis of it is going to be to break the motion down into vertical and horizontal components that will help us to determine the range of the shot, as well as the impact velocity that it makes. And eventually we're going to get into some World War I history and some kind of intimidating things from there. So let us move on to some specific examples from our homework right now. Okay, so we're going to move to our handout for today. In the diagram below, you see that we have something similar to the animation provided by physicsclassroom.com. And what we find is that we've got a projectile recorded at 5 points in time and even 1 second intervals. And again, notice that the horizontal velocity vector arrow remains the same size, whereas the vertical one keeps getting longer, indicating that the velocity vertically is getting greater and greater. And also note that the path of these particular projectile dots follows a parabolic curve. So this one is shot off a cliff that is 122 meters above, and we've launched horizontally at 20 meters per second. Horizontal projectile motion problems typically ask things like, how far from the base of the cliff does the projectile go, and what is its impact velocity? And this we'll have to consider in the x and the y, as if you had fired an arrow or something like that, it would stick into the ground, not vertically, not horizontally, but at an angle, which represents a combination of those two velocities. So let's get to it. The first thing I want to do in these problems is I want to indicate which direction is positive in the horizontal and the vertical. And to do so, I'm just going to, a little bit on the corner of my problem, indicate that down and to the right are positive. That's going to save us some time when we get into the kinematics section, saving us having to put everything into square brackets, and having a declared plus or minus makes algebra a whole lot easier. We're also going to break our information into horizontal and vertical components. So I'm going to make myself a bit of a chart here. I'm going to split these down the center into vertical and horizontal information. So I'm going to put my horizontal right here, my vertical right here. H and V is sufficient, in my class at least, to let me know that that's what you're thinking. Horizontally, we only have 3 pieces of information, in that our velocity is constant and there is no acceleration. So there's no V1 or V2, just our horizontal displacement. Our vertical displacement is on the other side. Okay, so we'll split up that information over here. So we have a few different things to consider. We have our vertical accelerated motion, and we have our horizontal constant velocity. And again, please note this is a high school version that does not consider the very real effects of wind resistance. So horizontally, we want to know what our range is, and so that's going to be one of our unknowns. Our velocity horizontally, we consider to be 20 meters per second. And we'll consider that accurate to 2 significant figures here. We're kind of plus or minus at least a meter per second. And then vertically, we're assuming that we're launching from 122.5 meters above the ground. Now I recognize that from the diagram, you could probably guess that this has got about 5 seconds of hang time, but you won't automatically know that because you won't automatically have a diagram that breaks it down for you like this. V1 horizontally was 20 meters per second, but vertically it is 0. And this is often a jump that students struggle with, but if you launch something horizontally, its initial vertical velocity is 0. It's not going up, it's not going down. A moment after it's launched, it will start accelerating downwards. Its velocity will start increasing from 0 in the downwards direction, but it won't be 0 for long. V2 is another stumbling block for students because all of our acceleration equations assume a constant acceleration, in this context due to gravity. And yes, of course, it stops when it hits the ground, but there's a brief, sudden, and if you're experiencing it, very painful acceleration in the opposite direction. So our V2 is actually unknown. That would be how fast this would hit the ground if you just simply dropped it vertically. Our acceleration due to gravity is 9.8 meters per second every second. Sometimes we write that as meters per second squared. And we don't know how much time it's in the air for. But what we do know is that these two times, given that it's considering the same object, are indeed the same. So how do we deal when we have two problems and we've got multiple unknowns in them? Well, we look for the ones that we can work with. So if we are looking at our vertical versus our horizontal, we've got a couple different equations that we could consider. And for horizontal, it's pretty straightforward. Our horizontal displacement is equal to our horizontal velocity times our time that we're in the air. Except for the problem is we don't know the range and we don't know the time, so we can't start here. Rather, we do have 3 pieces of information over for our vertical information. And so here we could start with an equation that doesn't give us V2. So that's the one thing we're going to ignore at the moment. But we have an equation that ignores V2, and it looks like this. Our vertical displacement is equal to our V1 vertically, which in this case is going to be 0, which will make our math a lot easier, times our time. Our displacement vertically is 122.5. It's downward, so it's positive. And our acceleration due to gravity is 9.8 meters per second every second, and time is what we're looking for. When we start launching things vertically, or at least at an angle, well, it's going to be a bit more complicated because our V1 won't be 0, and this could result in a quadratic. And depending on your level of comfort for mathematics, may depend if you want to use an alternate equation to get around this. But for now, this one's tidy because 0 times anything is itself. So 0 times anything is itself, and so we're left with 122.5 is equal to 4.9 t squared. We're going to isolate that a little bit more. We're going to divide both sides by 4.9. And so that's going to result in time being equal to 25. Now, that's time squared is equal to 25. To undo a square, we take a square root. And so our time in this case works out to very tidily 5.0 seconds. That is the same time, remember, as our time vertically, as it's the same object. So now that we have the time, we can now substitute that in to our horizontal information over here. So our horizontal range is equal to our horizontal velocity times our time. So we find that we have a horizontal range of 100 meters. And of course, this will be accurate to as much accuracy as we put into our initial data. And so we're plus or minus a meter per second. We'll probably only be accurate to plus or minus 10 meters here. Again, that's an approximation. Rules for that will be a bit more detailed as you get older. We've got our range, and that's pretty tidy. The next thing we need to find is our impact velocity. Okay, so if our impact velocity is a combination of velocities, well, we know how fast we're going horizontally, and that doesn't change. But our vertical velocity is currently unknown. on impact. I'm going to continue on my vertical section. Now, what if I made a mistake on time? If I use time in an equation, then that would result in a wrong vertical impact velocity, and that would lose some marks. So I'm going to use an equation that doesn't use time, just in case. So our final vertical impact velocity squared is equal to our initial velocity squared, which in this case was 0, plus 2 times 9.8 times our height of our cliff above the horizontal field. V2 squared is equal to about 2,400. We'll include the one just for fun. So we're going to discover that V2 is going to be 49 meters per second. And just to emphasize the plus means down, I'm just going to remind myself that here. So I now have two velocities. I have a velocity downwards, and I've got a velocity horizontally. These two together will result in my impact velocity. How do I combine those? Well, we've got experience adding velocities. Technically, we've actually got more experience breaking down a velocity into its components. Here we have its components, and we're going to build it back up. So I'm going to try to draw these approximately to scale. And so my V impact is going to be downwards, something like this, at 49, and horizontally at 20. So I'm going to try to make this roughly a 5:2 ratio. And so my impact velocity, I'm going to draw here in red. So it's not going to come down vertically, and it's not going to be traveling horizontally. It will hit at an angle. And to find our V impact, we're going to use Pythagorean Theorem. And so if we have 20 on the bottom, and we have 49 on the side, now, at least in my physics classes, you don't have to show your work on Pythagorean Theorem. Just draw a nice triangle, and that will be sufficient. And so if this is the case, we have 49 and 20. My hypotenuse right here would be 53 meters per second, rounding to the nearest meter per second. But I do not yet have an angle. So I know that I'm going to measure my angle from vertical here. So it would be down so many degrees forward. Sometimes we talk about the number of degrees from vertical, and that would be sufficient for this problem as well. Tan of our angle is equal to our opposite over our adjacent. So if we take the inverse tan of that, we discover that that is approximately 22 degrees, rounded to the nearest degree. It's going to go in here. So what is our range and what is our impact velocity? Our range is 100 meters, and our V impact is 53 meters per second, 22 degrees from vertical. That's how we solve for our first one. Now we're going to move on to our second one, and that's the one that's a little bit more intimidating. In World War II, bombing was much more sophisticated, but in World War I, planes initially were reconnaissance, and they used some dirigibles for bombing. Particularly the German forces were able to master dirigible technology and bombed London in World War I, which is less well known than the Battle of Britain in World War II. But soon, technology improved, and initially I believe French developed, and then soon copied by other forces. A flechette, or that's French for dart, was developed that if dropped from a height would get going so fast, I'm told it could break the sound barrier. And if you got high enough, you could certainly have enough potential energy to provide that. And so this is a picture of what that would roughly look like. I'm told that there were approximately 250 of these darts in a box, and they would be released from a moving airplane at height, and they would go very quickly. So if one of these early biplanes, for example, the Fokker series, again, be careful how you pronounce that, they would fly initially around 150 kilometers an hour, maybe a little bit more, and they could get up around 3 kilometers high. And so if you bomb from that height, how far in advance of the trenches would you have to launch your arrows from in order to expect to hit? Obviously, it would have to be before you were over top of them, otherwise you would miss. Then the more disturbing question, how fast would these flechettes come in? And given the amount of fear that this would cause, it would certainly suppress enemy fire from down below. In the beginning, people would take pot shots at the planes flying over the trenches, but that was much less appealing when a hail of silent but deadly darts were about to potentially come down on you. Okay, so our information here, traveling at approximately 150 kilometers an hour, 3 kilometers above the ground. Seems fairly modest by today's standards of bombing, of course. But how soon before we got to the trenches would we have to launch these darts, and what would their impact velocity be? Well, again, we need to break up our information into our vertical and horizontal. I'm going to want to indicate what directions are positive and negative in this case. And so right is positive, down is positive. And so I'm going to assume that I've got a plane. Please forgive the drawing. Is going in this direction, and our troops are down below. So I'm looking for a couple of things. I'm looking for our impact velocity. So what is that? And I also want to know what our horizontal range is. For DH, I want to know how far you want to release the flechettes in advance. If you stick around, you'll see some fun that we had in physics, launching some of these from the roof of our school. So, our information first. Well, vertical and horizontal information. So if our horizontal information goes here and our vertical goes here, again, horizontal information ignores wind resistance, so this makes things relatively easy. So 150 kilometers an hour, be really careful about your units, because 150 kilometers an hour, while metric, it's not SI. So work this out in advance. It's about 41.7 meters per second. If you forget how unit conversions work, that is an earlier lesson that we did in class. Okay, so we're going to ignore the 150, lest we end up with an answer that would look like things were going way faster. And time is unknown, but it will be the same as over here. Vertically, this is accelerated due to gravity. And so we don't know a couple of things. So we don't know our time. Okay, and so these are the same time though. Now our vertical displacement we know is 3 kilometers, again metric but not SI, 3,000 meters. There's 1,000 in a kilo. Our V1 vertically is 0. Again, be careful that you don't make the mistake of confusing our horizontal motion with our vertical. And V2, well, it's going to be important to figure out. Really make sure that this is not a 0, because while it does stop, hopefully not in an unfortunate soldier below, but it will stop, but that's not acceleration due to gravity, that's a sudden acceleration due to impact. And so we're just interested in its velocity while in the air. So it's acceleration due to gravity. You get an extra 9.8 meters per second every second traveling downwards. So let's go find the range, and let's go find the impact velocity. Time is the key, as always, in these projectile motion problems, to connect the horizontal and vertical information. And so the first thing I'm going to do is I'm going to work on finding time. And again, if this is 0, then our equation displacement is equal to v1t plus 1/2 at squared. Is a really nice shortcut, because all of this is going to be equal to 0, because 0 times t is 0. Our vertical fall for these flechettes, if they were dropped from 3 kilometers up, would be 3,000 meters. This will develop a terrifying amount of velocity. 1/2 times 9.8 times time squared. As we work that out, 3,000 is equal to 4.9 t squared. As this comes to the other side, we divide both sides by 4.9. For the sake of space, I'm not going to include that step, but we're looking at 612. We root both sides. And what we find is that our time works out to approximately 24.7 seconds. And if you're thinking, wow, that's a really long time, that would go really fast. You're absolutely correct. But first of all, we want to figure out how soon, well, it'd be 24 seconds soon, before the pilot was over top of the target. But how far in advance? What would the horizontal range be? And so this, once you've got time, is one of the easier parts of projectile motion to calculate. Its horizontal velocity is 41.7 meters per second, and it's in the air for almost 25 seconds. If you multiply those two things together, discover that this would have to be released just over a kilometer before arriving, which would be a very difficult task. That being said, the trenches were fairly long. They stretched all the way from the English Channel all the way to Switzerland, and they did zigzag a bunch, but these things would spread out from a height like that and cover quite a distance. They were quite scary. So I'm not exactly sure how accurate that would be, but you'd want to release it about a kilometer in advance. So that is our horizontal range. That's one of our answers done. More involved is finding impact velocity. And so if we're going to find our impact velocity, the first thing we need to do is find our V2 vertically, and then we'll combine it with our horizontal velocity. So if we just drop this from, say, a hot air balloon, what would the impact velocity be vertically? Well, again, you don't have to use this equation because you have time now. But should you have made a mistake on time, maybe you forgot to do the square root, for example, and you had 612 seconds in the air, maybe 10 minutes of falling. These darts, in that case, according to your calculations, would be going ridiculously fast, breaking the sound barrier many times over, and would result in an incorrect estimate for your impact velocity. So I'm going to use one that doesn't involve time just to avoid that, just in case. My V1 is 0, which is also handy mathematically. And my acceleration due to gravity is still 9.8 meters per second every second. And the vertical displacement right here is 3 kilometers, or 3,000 meters. So if we ram that through a calculator, V2 squared is going to be equal to a really big number here, 58,800. And we'll have to square root both sides. And so we get a vertical impact velocity of somewhere around 242 meters per second. And if you're thinking that's fast, you're right. At 242 meters per second, just vertically alone. If you multiply that by 3.6, which is just a really quick conversion trick, these would be going at about 800, almost 900 kilometers an hour. And that's before we consider the horizontal component. Final part, V impact. We have to consider both of these velocities together. Now, our vertical is 242. I'll represent that by a red arrow right here vertically. And our horizontal was 41.7. So that's much more modest in comparison. So I'm going to draw that as a shorter arrow. What's our impact velocity? Well, we're going to want to combine these two together. So that's what that green arrow is going to represent. So my hypotenuse is my V impact. And if this side at the bottom is 41.7, and our vertical velocity here is 242, we'll discover this is a pretty skinny triangle. I should have actually made the 41 even smaller. And what we find is that our V impact here is about 246 meters per second, but we don't have a direction yet. And so again, you have opposite and adjacent. You use tan. And to get that by itself, you would use inverse tan. second function tan. What I find here is that it's about 10 degrees. So this will be 10 degrees from vertical, down 10 degrees forward or to the right. And what this meant for the rank and file on the ground was that these things would rain down from the sky, and they would be not quite vertical, which meant that even if your helmet might protect you, and these things tended to have enough momentum, a sharp enough point, that even a steel Brody helmet wouldn't be sufficient, but it could also miss your helmet and cause really terrible injuries. Apparently the British tested on a cow at the beginning of the war, and after dumping a whole box of these things, 3 of them actually impacted the cow. All 3 of them went through the cow into the ground, and the cow died very shortly thereafter. I am super thankful that these ideas of flechettes are history and not something that I experience. But lest we think that this is ancient history, recognize that flechettes were actually used in Vietnam and Korea. And so these weren't just things from over 100 years ago, but these are still capable of being used, and they're very effective in regions where there's a lot of foliage. So we'll cut to some footage of flechette flying again for the first time in 100 years, an experiment that we tried to replicate at my school from our roof. Enjoy.
In physics, we're trying to fire off some World War I flechettes, or airborne projectiles, to see what they will do when they fly down from the top of the school. Mr. Dykeshorn is assisting. Okay, Mr. Dykeshorn, you ready?
Yep.
Fire at will. And so that's what these things would have looked like after falling, except they would have gone a lot faster.